we'll have separate chapters where we talk about exercise and chronic as well. Okay, so we're at the point where we're talking about myocardial oxygen consumption. And so this gives you an idea of how hard the heart has to work. And so whenever you do exercise, the heart has to work harder to deliver oxygen, to deliver blood, and deliver oxygen to the working tissues. And so in doing this, the heart has to work harder as well. So a means of measuring how hard the heart is working is calculating rate pressure product. And that's taking systolic blood pressure and multiplied by heart rate. That gives you a number, which is your rate pressure product. And so if you're doing something with really high systolic pressure and really high heart rate, then you're going to have a really high rate pressure product, so that heart's working pretty hard. So if you think about that, think about the difference between resistance training and aerobic, like resistance work and aerobic work on the heart. And looking at it from the viewpoint of rate pressure products, you're really not going to have a high rate pressure product with resistance training. Just because you're going to have a large increase in systolic blood pressure, but you're not going to have a large increase in heart rate typically. And as soon as the exercise is over, you may have a little higher heart rate, at least initially. Systolic blood pressure is going to drop. So rate pressure product isn't huge, as you might think. Now there was one study that did valsalva with the leg press, and blood pressure got up to like 480 over 350 or something like that for a short period of time, or 420 over 380 or whatever. So yeah, the rate pressure product is probably pretty high, yes.
Has there been any tests with maximal efforts like that on the leg press included?
So like the Katsu type something, cut off blood flow and on the effect of blood pressure? Yeah. No, I thought, maybe. Talk about killing people in research,
That's kind of what I do with those.
But do you do the Katsu training with the leg press?
No, I think the equipment that I wear, under maximal squats.
Oh, yeah, it does restrict blood flow. But I mean, I don't know. Well, I tell you, you can wear your outfit where you measure your blood pressure. And we'll have to get some better instruments, maybe a press or something like that, so we can get kind of consistent blood pressure or constant blood pressure. But yeah, I don't know. But that rate pressure product you typically see with resistance training. Well, with aerobic training, you get a typical drop in rate pressure product at a certain intensity. So, like running at 6 miles per hour before and after training, you're going to have a lower rate pressure product because typically you're going to get a reduction in sympathetic blood pressure at a certain absolute level. And also heart rate's going to be lower at an absolute level. So rate pressure products are going to go down to get an absolute level of performance. And same with resistance training as well. And that rate pressure product is going to drop faster after exercise. So same with resistance training, you get a very similar effect. So decrease rate pressure product at the same absolute level. But who does anything in resistance training at the same absolute level? It's all about more weight. So yeah. So rate pressure product, just remember, as far as calculating workload on the heart, rate pressure product. Okay, and stroke work, that's the external work done by the left ventricle in one beat. So stroke work. Which can vary depending on the type of activity. So you have activities that you have an increase in preload, and you have activities that have an increase in afterload. And so that's going to affect the stroke work. So, show you what I mean. Oh, there we go. So you have flow work and you have pressure work. Flow work is increased work due to increased preload, like running, aerobic running, jogging, things like that. Pressure work is increased work due to increased afterload. So hypertension, if you will. And so if you think about it, you may have the same forces being generated by the heart, but some of the forces produced with flow work is done through the elastic elements within the cardiac muscle, so it's the Frank Starling mechanism. So you get a lot, very good return of energy with cardiac muscle. It's got very nice elastic elements. So flow work, you're not doing as much work, if you will, or at least the heart's not having to do nearly as much compared to pressure work. So you might be, the product might be the same as far as pressure generation, but you're having elastic elements of the muscle because of the increased free lift aid in the work being done. So the actual energy that you need to produce that force is less with flow work and pressure work. Let me ask you this, just kind of a thought question. You read about adaptations to the heart with different types of training, so aerobic training versus resistance training. And there's some evidence recently to show that the differences aren't that great between resistance trained athletes, aerobic trained athletes, and the heart. Some studies have shown that there's, with resistance trained athletes, there's some studies that show no changes to the heart as far as being different from just controls, so people that don't exercise. And some showing adaptations that you might traditionally think of from resistance trained athletes where you're dealing with typically you're doing pressure work because higher afterload during resistance training. And you might get the not only increase in cardiac muscle, but also increase in wall thickness as well, because the two don't necessarily have to go together. And then you get some that you get the adaptation where you get increase in muscle, but not increase in wall thickness. Pretty much means you're increasing compliance. You get stronger muscle, but you're increasing compliance as well as thickness of the muscle. Comparing resistance training to aerobic training, why do you think that you might not get either as much of an alteration or even a similar alteration between resistance training and aerobic training? And people don't know for sure, so that you're not going to give a wrong answer, maybe a stupid answer. Yeah, just kind of, what do you think?
What kind of resistance training are we talking? Like power, like 1 rep, or like
No.
10,
So this is like we're real world here. We're MTV, the real world. So we're doing a real training program, like say what you do, but I don't know what you do, but I would hope that you do something, whatever. Some periodized program. So if you just wanted, if your cousin was just like, I'm not an athlete, but I just want to get stronger, get me stronger. And you can ask a bunch of questions, try to get goals and things like that, whatever the sort of program. But either way, you just some standard resistance training program for your cousin or something. And then you measured, but we brought them in here, and we're going to sacrifice them at the end of the study, so whatever, just to check out the heart. But we measured cardiac dimensions before, and then cardiac dimensions after with our ultrasound. Why do you think and his identical twin, the good cousin, did the aerobic program, so they want to do aerobic exercise, like a bad cousin. And so, yeah. So what do you think? What do you think the alterations might be different terms?
I mean, this is probably the super general way to start, but does it have to do with any, just like the overall load? Because an aerobic workout, it's going to be low intensity, but it's going to be, an appropriate duration.
Are you saying resistance training is not appropriate duration?
Well, no. I mean, it's going to be like an equal stimulus with the rest periods and the work periods and.
Well, yeah, no, and that's a question raised by researchers. It's like, well, you're going to have to set up your resistance training program to mimic an aerobic training program. If they're going to run for 20 minutes straight or 40 minutes straight, an hour and a half straight, that's an hour and a half worth of that stimulus on the heart, worth of that flow work. And so that's kind of what I was getting at. Versus resistance training, it may take me an hour to get my workout in, but in reality, as far as you count the actual time that I'm doing that, not that much at all, really. And then even I'm doing sets of 10 or 5 sets of 5 or something like that. But then, what am I doing as soon as I get done when I re-rack that weight? I'm breathing heavy. My heart rate is up. I'm aerobic. So it makes sense that you're not going to see the same adaptation. Or you'll see pretty similar adaptations because you're dealing with a pretty short period of time with that resistance, that pressure work is done and then a lot of floor work after that. And it may not be because you have increased preload, but you definitely reduce the afterload. So and then we can look into, as soon as you get done, you get a cycler governor pedal so you can increase that preload. Whatever. But yeah, so I mean, it kind of makes sense that you're not going to see these drastic, differences. Like if we did, what was that article that Doc just sent out? The person doing 148 repetitions of bicep curls and end up with rhabdo or something like that. 148 repetitions of squats and see what happens. Whatever. But yeah, so I mean, it kind of makes sense if you think about it. So I mean, just kind of thinking about outside the box a little bit.
We wouldn't have to kill people to see heart dimensions. Like we could this is more me.
But if you want to,
ignorantly, like
I know some homeless people.
Can the ultrasound do that?
Yeah.
So is it I guess in studies, is that how they typically do heart dimensions?
Yeah, you can look at heart dimensions are typically done through ultrasound. So we have a cardiac probe now, so we can do that. So we can, without killing anybody, we can look at. But I've got a list if you want. But we can look at we can look at left ventricular dimensions and wall thickness with our cardiac probe. And we can also so we can calculate cardiac output, stroke volume, and diastolic volume and systolic volume with that. We can also get the aorta as well. So we get aortic dimensions, so we can calculate stroke volume with the aorta as well, because you can look at rate of flow and the size of the aorta and calculate the stroke volume of that as well. So you can look at stroke volume a couple of different ways. Plus, you can look at the anatomy of the heart.
And what's the difference between the two probes then? Like, what does the cardiac probe do differently?
The cardiac probe is really narrow, so you can get between the ribs. And you've seen those typical probes that got pretty wide and pretty muscle. So yeah, it's the probe itself can read between the ribs. And two, there's software programs to go along with that, so you can get it'll help automatically calculate those dimensions and diastolic volume, systolic volume, things like that. So it's kind of nice. So we can do that. I'd love to do that. I need to get down here and play with that stuff. But yeah. But just think about stuff like that, and like you're talking about reading the research, kind of reading into it, kind of looking at it. You have your own perspective of how you look at it. But it's kind of when you have problems that you're looking into, kind of put some thought into it, going, well, why, from a big picture standpoint, why are things the way they are? So put a little thought into it to kind of figure it out. Okay, finishing up the slide, and we already talked about myocardial O2 consumption going to be higher in pressure work than flow work, even if the output's the same, even if you're generating the same amount of pressure, because O2 consumption has to do with ATP regeneration, and so if you're getting some of your work being done through the elastic elements and not all through ATP utilization breakdown, then this is going to require less O2 consumption than this, even if you have the same outcomes as far as stroke volume, pressure generation, and things like that. So yeah, and so that rate pressure product is used to estimate myocardial relaxation consumption, but it also depends on flow work versus pressure work. It's like the exact so ventricular pressure volume loops. So this is a Wicker's diagram type deal, looking at you have your ventricular volume, so you got that increase in volume, the slight increase in pressure as it's filling, and then you get that isovolumetric contraction, so no reduction in volume until it overcomes the pressure in the aorta, and you start injecting blood rapidly and then slowly, and then the aortic valve closes to get that isovolumetric relaxation until you get the opening of that mitral valve to allow blood flow back into the ventricles. So that's your pressure volume loop, and we're looking at differences and if you can increase preload, increase afterload, increase contractility, and what that does to the pressure volume loop. So increasing preload, obviously, increasing force of blood flowing into the heart, so you're getting higher volumes. Doesn't change the aortic pressure, so you don't have to increase pressure above what you normally would. And so, if you can imagine, if your stroke volume, well, there's your stroke volume right there. So you're getting an increase in stroke volume by increasing preload. Added that to your stroke volume. Increased afterload, you've decreased stroke volume. So there's your stroke volume initially. There's your stroke volume now. And so you got to generate more force because you have a higher pressure in the aorta that you've got to overcome, and that's going to cause it to close faster. because you're going to get down to that little higher pressure. So it causes an early closing, and so just less filling, so less of a stroke volume, and do more work, generating more work here to eject blood out. So decrease in stroke volume. And that's not, this is all you're doing. You're just increasing preload, just increasing afterload, or increasing contractility by increasing sympathetic stimulation. And so increasing force, because this is a measure of pressure, it's a measure of force that you're generating. So increasing force rush. And with that increased force, you're ejecting more blood from the heart. So with increasing contractility and increasing preload, you've increased stroke volume. So if you remember that slide we talked about, what increases stroke volume, you see contractility has, because that's altered the stroke volume. Preload is also done a little different way. So you can increase in diastolic volume here. This is in diastolic volume and systolic volume. Here you decreased in systolic volume while maintaining in diastolic volume. And here you decreased in systolic volume without increasing in diastolic volume, so you've decreased stroke volume. So I've got the slide that explains how you increase stroke volume, preload, contractility, how you decrease stroke volume, increase afterload. So just a little graphical representation of what's going on with that. Fish. That's not Italian for understanding. Lower. As far as cardiac muscle cells, the more you stretch them out, the more elasticity they can add to the force production. So they're very efficient when you stretch out the cardiac muscle. However, when you're dealing with a cylinder, like the left ventricle is, there's that law of Laplace where tension developed equals pressure times the radius divided by 2. Math magic. But ultimately what it's saying is, you're going to get to a point where you're going to get a dimension that's so wide you've got to generate, too much tension to be able to get a, we're not economic contraction, but efficient contraction, if you will, or whatever. So you can't get too large, and which is probably why that combination of filling time, which is why stroke volume tends to level out instead of increase all the way up through max exercise. Now, in some populations, like especially in highly trained athletes, they've had some studies to show that highly trained athletes get that increase in stroke volume all the way up to max. It's not perfectly linear, but it's kind of funky, at least in the studies that I've seen, versus leveling out. Could be that they've got larger muscle mass so they can handle the larger dimensions of the left ventricle expands. And they also have very efficient blood flow. So you get more precise matching of blood flow reactive muscle, so you get a much better muscle pump, better venous return, better preload, so they can increase that stroke volume all the way up to max.
Does the Frank Sterling mechanism counteract that?
Oh, it does, but that's what the muscle cell and not so much a whole organ. I'll have to look at this. I'll see. Got a nice textbook that explains this. I'll see if I can get a better explanation of that. But this law of Laplace is one of those things where it's the reason why your heart, you're going to get to a point where it's just not as efficient, and you have this huge heart that can expand. This one explanation why stroke volume may not rise all the way up to max exercise, but also that filling time increases, which is why stroke volume may not increase all the way up to max exercise, unless you're very highly trained and genetically gifted aerobic athlete. So you get very good matching of blood flow to the muscles, and so very good muscle tone. Also higher muscle volume or higher blood volume. Regarding the pericardium, pericardium is that sac that the heart sits in, fibrous sac. There's fluid surrounding the heart within the pericardium, and the heart kind of sits in this. It goes sits in that pericardial sac, and so it limits how much the heart can expand. Now you can increase the size of that pericardial sac through training. But you can also just cut it. They did this with greyhounds. Who likes dogs anyway? Yeah. So, whatever. And so they took these greyhounds and they did before, which is in, and after the pericardectomized dogs, so P for after. And they looked at stroke volume. Same heart rate before and after. Higher stroke volume, so higher cardiac output, so higher VO2 max. Now the VO2 max actually wasn't, you figure you get about that big a percent increase in VO2 max, but you actually didn't see it because in the study, the problem was, during the surgery to cut the pericardium of the dogs lost blood volume, and so lost red blood cell content, which they didn't replace. And so it's kind of like giving a pint of blood and, performing a marathon, giving a pint of blood and performing another marathon or, max test or something like that. You're just not going to have the oxygen carrying capacity afterwards. And so they didn't see the same increase that they thought they would based on the difference in stroke volume. But they did see increased performance. Now, I think they had mentioned in this study that the long-term effects of that would be bad because the pericardial fluid leaks out and you could get scarring of the heart, and that could, decrease the pliability of the heart, lines of the heart. So yeah, but there you go. Pericardium and stroke volume levels. You cut the pericardium and increase VO2. Well worth it. If you're an aerobic athlete or you coach an aerobic athlete, you may want to talk about it. So with that, if you increase stroke volume, you should increase VO2. And they did. They just didn't say it's the same extent because of the blood volume. So measuring cardiac function, how do we measure cardiac function? I've talked about this a little bit. John kind of asked about that as well. So heart rate's easy to measure. So if you look at cardiac function and you want to look at cardiac output, stroke volume, heart rate is pretty easy to measure. It's stroke volume, that's not easy. So measuring systolic function, ejection fraction and heart failure patients, they do it. They typically do it through echocardiography. So the triple dimensions are measured, and volumes are calculated based on geometric assumptions. So because you're getting a one-dimensional view of the ventricle that you're drawing out, but because the computer has a program that knows that it's a cylinder, so it can apply calculations to that based on the size of your outline and give you the volume that's in there at the end of diastolic volume. And you can do the same thing in systole, you get in systolic volume. From that, you can calculate in diastolic volume and systolic volume, stroke volume, ejection fraction, and things like that. So ejection fraction is used in heart failure patients, like if you're 40% or less as far as stroke volume or ejection fraction, that's a diagnosis for heart failure. If you're 35% or less, that's a diagnosis for putting you on the heart transplant criteria. So there's a heart. There's a picture of the heart. See the chambers. Picture of ventricles. But in this, you would take this little, just like you would with the skeletal muscle you outline. You just outline the ventricle. Would apply your little mathematical formula to estimate the volume within that ventricle and calculate in diastolic volume and systolic volume. So that was at rest. Exercise a little tougher, but we can do an exercise as well with our with the ultrasound device, so like the cardiography, but then ultrasound. So we have a Doppler flow probe. So it measures blood flow velocity, so it lights up its different colors, and based on that, the computer knows how fast red blood cells are flowing. So it knows flow rate, it knows dimensions of the tube that it's flowing through, so it can calculate stroke volume that way as well. So you can do it in the aorta or do it the same way where you're measuring in diastolic and in systolic volume. So you're basically taking a recording, and you could scroll the video forward and backwards to get to the point where you got the maximal, the in diastolic volume, and then same with the in systolic volume. Take your measurement string exercise, yes.
What's CHF?
Heart failure. Congestive heart failure.
Got it.
So some systolic function, measure of the heart's ability to check blood. So you have fractional sorting measures, ejection fraction measures, so percent change in left ventricle dimensions with each contraction. Calculated that way. Ejection fraction is probably more popular. Stroke volume divided by left ventricular diastolic volume for ejection fraction. So 55% rest, typically up to 75% during exercise. It's a pretty standard ejection fraction. Like I said, if it drops below 40, that's criteria for heart failure. You can do all this stuff. I just need to play with our life. We may bring it in here and just lecture somebody. If anybody wants to pray, and that's the next one. Questions, comments? Anybody? Next, we're going to do, cardiac myocytes. So on Thursday, we'll do cardiac myocytes. The next one. Questions, comments? Everybody out.
Dr. Ramsey, I'm presenting next Tuesday or Thursday?
Are you next?
Yeah, I'm next. Do we present on Tuesdays or is it just for the week? Thursday? Okay.
Are you prepared to present this Thursday?
Yeah, I can present.
Oh, can you?
Yeah.
Thursday.
Okay, that works.
Who's next? Who's next to go? So Tuesday.